Okay. This is the one that throws people off because they were never, or at least in my experience, I've seen people not get taught this in class and therefore have no idea how to do it. But this is the same thing we just learned completely in reverse. The time of tide at any height. This is actually probably more realistic that you would need this, because finding height of tide at any time would be like if your ship was scheduled to come into port at a specific time and you wanted to know, hey, what will my tide be? Sure, that's fine. But if the water is deep enough that you're not really that concerned, that's really the only reason why you would just be looking into it, but you wouldn't be setting any any boundaries on what it has to be. What this problem is saying, though, is imagine your ship is a really deep draft or you're coming into a really shallow port and you are legitimately very concerned about the water under your hull. And you say, hey, I need a safety draft of an additional 3 feet under my keel. And given the depth of the water, the height of tide needs to be 3 feet for that to be possible. Like the depth of water is equal to your draft. So to get an additional 3 feet, the height of tide has to be 3 feet. It won't always be that perfectly worded out, but that's one situation you'll have. So you need to look up and find at what point in time in the day will the water be at least 3 feet, if not getting deeper. That's what these questions are asking. So it is probably important to understand how to do it. So in this problem, this is not one that you can just make up in your head like I did with the others. For this one, I took it out of a question packet. At what time after 1400 on January 4th will the height of tide in Port Wentworth, Georgia be 3 feet? So when will it hit this height right here? The reason they specified 1400 on Georgia, or on the 4th, is because there's probably another point earlier in the day that it also does. But let's say your ship isn't going to get into port until the afternoon. So you don't care about that earlier one. You want the one in the afternoon. I also marked this over here that the question specifically noted that this is in ZD plus 5. Questions will do that a lot to throw you off, because all of the East Coast is in ZD plus 5. That's nothing new, so this shouldn't bother you. But every once in a while, they will put ZD plus 4 to tip off to you that you're using daylight savings time. And if you have a question asking daylight savings time, all you have to do is you add an hour to every single value that's listed in the main station, because everything is now an hour later. Don't worry about that for this problem because it's ZD plus 5, but make sure you take note of that zone description. It doesn't just not matter. It could be used to lay a trap if it is daylight savings time. If it's not, though, then you're good. All right, how do we begin this problem? Well, we actually start off in exactly the same way. We still start off finding the information for the substation. Meaning, if you want, I'll set a timestamp as well, so you can just skip to when it's actually relevant to you. So we come down. To our index. And we're looking for Port Wentworth. It's going to be tons of ports, so it's going to be hard sifting through all this. Port Wentworth, Georgia, right there. You can see we got reference number 2715. So we'll write that down just like we did before. $2715. Okay. Now we come back and we start to look for that. So I skipped to 60 before. Let's try 70. Oh, never mind. All right. We're in the 3000s here, so we got to move back upwards. 28, 28, 27, 2715. Port Wentworth. And I think there's an ink stain because it looks like Fort, but it is Port Wentworth. Where'd it go? Right there. Port Wentworth, Georgia. You can see it is on Savannah. So Savannah is our main station. Step one, though, we got to copy down these correction factors. So we set up the table again. There's our table. And now we're going to copy it down. First, let me write on Savannah. And I guess this is useful to make note of. In the substations list, they will actually list the main stations as well. They won't give any correction factors for them, but they'll say, hey, if you're looking for Savannah, go to Savannah. That will give you the times. But for Port Wentworth. So its times are plus 33 minutes and plus 41 minutes. Yes. So you come here, plus 0.33, plus 0.41. Now its heights are minus 0.4 and 0. Remember, minus 0.4 and 0. Remember, the vertical datum for a station is based off of the mean lower low water. Mean lower low, meaning if you take all the low waters in a day, because there's usually two, you take the lower of the two because they're usually a little bit different, not much different, but a little bit. You take the lower of the two, so the lower low, you take the average of all of them for all of time, and that will give you the mean lower low water, which is what the datum is based off of. So it's also the most common low water. Realistically, it's the mean. It's close to what you can usually expect, which is why lots of times your low water corrections are 0, because they happen to be fitting the mean at that moment. Okay, now with this information, now we can go to our main station. So we're headed to Savannah on, 4th of January? So we'll come up here. Let's try Savannah. Here's 70. Suriname, way too south. Mayport, Florida. It's pretty close. Savannah, Georgia. And there's Savannah, Georgia, January. Okay. 4th of January. Right here. So, again, if you're finding the height of tide at any time or the time of tide at any height, you only need the two times that fall on either side of your desired, so the one immediately before it and the one immediately after it, which in this case is 1247 and 1939. But as practice, we're going to take all four again. So let's set up the table. Savannah. Okay, here's our times. Here's our heights. So our first time 033, 0033, and it has a height of 7.2 feet. Then next, 08, this is really hard to read. It might be 06, that makes more sense. 0648 at a height of negative 0.7. Then 1247 at a height of 7.8. And 19, God, I hope that's a 3. 19, no, it's a 1. 1919 at a height of negative 0.4. Even if it were a physical book and not a computer file, for whatever reason, the tide tables are still, they're just scans of really old, of, a catalog published in 1983. So there's a lot of stains and like ink blobs that make some of these numbers really hard to read. Anyway, here are our values. So now we just need to apply the corrections over to, what is it again? Port Wentworth. I'll just write PW. For time and for height. So let's start with our high tides. Our high tides have an additional, happen 33 minutes later. So 33 minutes later, and they are 0.4 inches lower, or feet lower, sorry. Our low tides are 41 minutes later, and they are no different in height. Now we correct everything across. Remember, we only really need these two, so these are the two that you need to be focused on the most, but we'll do everything for practice. So 0.33 minus 33, that's cool. We get balls, minus 0.4, 6.8 feet. 648, I was so excited to get balls, but it's add, not subtract. So it's actually 0.106, unfortunately. 648 plus 41 minutes, you get 9, 8, so 20, so 0.729, no change in height, so negative 0.7, plus 33 minutes to 1247, you get 0, 4, 20, 1320, with a height, minus 0.4 of 7.4. Then 1919, add 41 minutes, so you get, oh, that's kind of cool. That actually comes out to 2000. And no change in height, so negative 0.4. By the way, as a quick aside, just when I was talking about the mean lower low here, 648 is the lower of the two lows in Savannah and in Port Wentworth. So those would be the ones that would go into the tidal datum. So averaging this out, this would reduce the average ever so slightly, by a minuscule amount. So we only need these two. We need the information off of these two. So, well, I'll start with the easy stuff. What do we need? Well, we obviously need the range and the duration of tide, because we need those two to go into the table. So we'll start with range. Between 1247 and 1919, we go from 7.4 to negative 0.4. So we'll do 7.4 minus negative 0.4, in other words, plus. So our range of tide is 7.8 feet. And our duration is from 1320 to 2000. 13:20. So that is, well, if we bring this up to 14, that's 6 hours. So 6 hours and 40 minutes. 0640. And that's nice because if you remember, our table is in units of 20 minutes. So that'll actually mean we'll land right on a line. That doesn't always happen. I'll talk about that in a second. Now, the next thing you would need is time to nearest. But you don't have a desired time. You have a time that is, you have a time, you know, it has to be after 1400, which is why we're working with what the numbers we're working with. But you don't know when this is going to happen. That's what you're trying to find. And normally these problems are about trying to find the change in tide that will happen at a certain time. Now we're working in the opposite direction. Now we're trying to find the change in time that will occur if you have a certain change in height. So what that means is instead of having range, duration, and time to nearest and using all of that to find your correction, you have your range, your duration, and your correction, and you're going to use it to find your time to nearest. So how do you find what your correction is? Well, we need the height to be 3 feet. And you know that your correction is applied from the nearest high or low tide in the direction necessary, or in the direction towards your desired time. So, for instance, 3 feet, we know it needs to be both after 1400, so nowhere near 1320. It has to be later in the day. And we know, based off of the range of 7.4 all the way down to negative 0.4, it's probably going to be like towards the later half of this change here that you'll get a height of 3 feet, just because it's much higher at the top than it is at the bottom. So you could say your correction is whatever it's going to take to go from, using all that, we're just choosing negative 0.4 as the closer of the two, so the nearest of the time to nearest. You're going to say, what does it take to go from negative 0.4 to, to 3.0. How much change needs to occur to go from a negative 0.4 height to 3.0? Well, you have to go up 3.4, right? Meaning if we're picking the low tide that's at 2000 as our nearest time, which we kind of have to be because the other isn't an option, then it would require a correction of 3.4 feet to get a height of 3 feet. Doing that, we now have three numbers that we can put into the table, meaning we can find the fourth. So our range is 7.8, our duration is 6 hours 40 minutes, and our correction is 3.4. We come back, what was it, like 239? Oh no, 139. Forgot I was 239 in the printed numbers. There it is. Okay. So the way we used this before is we started with our duration, which is the total time between high and low, slid out until we reached the time to nearest that we were looking for, then followed that column down until that column intersected with the range of tide that we wanted, and where those two intersected, that would be our correction factor. We are now working in the opposite direction. So we're going to start down here and work our way up there. meaning the first two we need is our range of tide and our correction. So we're going to pick the range of tide that's accurate to us, follow it across until we get a correction factor that we need. Then we follow that column upwards until that column intersects with the duration of rise or fall that we are looking for, and that will give us our time to our nearest, which in this case is the lower tide at 2000. So if we go back to our numbers, because I forgot, range is 7.8 feet, correction is 3.4 feet, duration is 6 hours 40 minutes. So we come down to the range, 7.8. Let's see, we have 7.5 and we have 8. Considering how close we're working with, like it's not a huge difference, we can go with 8. So we take our bookmark here just as a straight edge, and we follow the 8 row across until we get a correction of 3.4. Well, we don't have 3.4, but we have 3.2 and 3.6. Those are 3.4 is equally as close to either of them, so you could pick one and just go with it, or you could kind of split the middle and watch both. So I say we watch both, and we follow both of these columns up here so that we can choose later. So we line our straight edge up like that, and remember, now we're looking at both of these columns just to be safe. And we slide up, and our duration of rise is 6 hours 40 minutes. So you come across, you follow 6 hours and 40 minutes until you get to the two columns we're looking at. You could see one of them is 2:53, one of them is 3:07. 2 hours 53 minutes, 3 hours 7 minutes. Now we were exactly in the middle between the two. So honestly, if you chose either of them, you'd probably be right. You'd be off by 14 minutes at most. Well, you'd be off by 7 minutes at most. And no question would be that close that you could get it wrong. But let's be perfectionists and let's take the middle. So the middle here is exactly 3 hours. That also makes our lives a little bit easier. So to recap, we took 8 because 7, actually, if we go with 7.5, if we were to follow 7.5 instead of 8, which is slightly off, that would have given us 3.4 as an option. But let's commit to what we did before. So we followed 8 because 8 is closer to 7.8. We got 3.2 and 3.6. Because we couldn't choose between the two, we just followed both of them up so we could stay informed about both. Followed them up until they intersected with the 6 hours 40 minutes, and that gives you 2:53 and 3:07. If we want to, we can split the difference. Actually, though, now that I see that the 3.4 was on this column, that means it's probably closer to this being more reliable. Though that's that's when it comes in. We come into an area of subjectivity. So let's go with 3:07. So my computer just dropped. So our time to nearest we found is 3 hours, 7 minutes. Remember, that is the difference in time between our desired time and the higher low that we were basing our correction off of. We based our correction off of low tide because it was, you can just tell logically that the low tide was going to be the one that's going to be closer to the 3 foot mark just because it's so low down and the high tide is so high up that 3 is going to fall closer in time to this. So now we know that this distance in time, difference in time, is 3 hours, 7 minutes, and this is 2000. We're going back in time in this case. So now, to get our final answer, we just take 2000 and we go back 3 hours, 7 minutes. So 60 minus 7 is 53. 19 minus 3 is 16. And that is our final answer. If we want the time after 1400 on the 4th of January in Port Wentworth, Georgia, that the tide will be 3 feet, what you do is you get the information of the substation by going into the index, and then to the substation, you get all of its corrections. You go to the main station of Savannah, you get all of its information. You apply the corrections to the main station, that gives you the values for the substation. You pick the two that your desired time or your approximate desired time falls inside of. You use it to find your range and your duration and your correction. Because in this case, we're trying to calculate time to nearest and we have correction. Whereas in the other type of problem, we had correct time to nearest and we were trying to find correction. So you use your range, your duration, and your correction. You work the table backwards from the way it was originally used. And that will give you your time to nearest. And you apply your time to nearest to the low water in this case, because that is the one you're nearest to. If you were nearest to the high, you would apply it to your high. And that gives you a final answer of 1653. So to make it more realistic of what we're talking about here, let's say if the height of tide is lower than 3 feet, you will run aground. Now, because we are approaching low tide here, that means that any time after 1653, the height of tide is less than 3 feet. So what this problem would tell you is it would say you have the whole afternoon after 1400 until 1643. So you have nearly 3 hours where you can come into port and you will not run aground. But after 1653, you will not have enough water underneath your keel. So that's the time of tide at any height. This is really the most tedious of the tide problems you're going to get. But don't worry, currents are just as bad.